Swayam Prabha. Digital India. Educated India.
So after this whole heating process is carried out for about 85 to 90 degrees for about close to 45 minutes to 1 hour, you have a box kept here. So this was labeled in this particular leveling plate inside the oven, and you have quite uniform layer of PDMS which is solidified on the top of these structures here, which are made up of the laser machine PMMA surface. Okay, and so you have now what you were looking for. We are trying to build two different layers of PDMS. This is actually a thinner layer on the top of this mold, and both are equally important for the field of microfluidics. So this would be a thin layer PDMS. So subsequently I will show you another step where you have to do a thick layer. Use the normal paper cutter for the purpose of cleaving the mold box on all the sides. Remember, this box actually is a sacrificial mold box. It has to be at the end of the day, it has to be a use and throw kind of a platform. So we cleave all the corners of this box, and one thing which is important for me to tell you is that the PDMS is sticking to any surface quite firmly, especially when it is get cured, it gets cured, etc. And in this case, because we did not treat the surface of the mold box with this mold releasing agent, there is a tendency of the PDMS sides to stick to the side walls of the mold box. So one has to be extremely careful about removing this mold box and removing or extracting the molded PDMS along with the polymeric structure which is inside, the PMMS structure, laser machine which is inside, so that you can have the sides or the edges of this whole stamp uncleaved. Okay, and this is a very it has to be done very carefully to prevent any kind of cleaving action or sticking action of the sides of the mold box with reference to the or with respect to the PDMS inner. So you can see here the PDMS being extracted very carefully, and wherever there is additional cutting to be done, and in fact, one can, because that's why the box is designed in a manner which is always oversized than the size of the individual die which is going to replicate the device. Okay, so if need be, some sides and edges can be cleaved off. In any event, they are going to be cleaved off later once the extraction of the mold and subsequently the retrieval of the replicated part happens from this particular setup. So there is always a possibility that there is some kind of a infiltration of PDMS on the lower side of the PMMA mold. You remember when we did this fitment of the PMMA mold, although we put a sort of adhesive tape on the bottom, double sided tape on the bottom, still there is some gaps which are there, and there is a possibility of the PDMS to go on the back side of that mold, and when it gets cured, there is a rubbery membrane developed there also. So one has to be careful about cleaving that. So you have to really know very well which side is the patterned side. Okay, and then be careful by removing every other thing on all the different sides, like on the other surface, for example, of the PMMS where there is no pattern. Okay, so that surface, whatever film is formulated, you should typically cleave off, and those are all sacrificially used for realizing the most important, which is what the film that is formulated on the top of the patterned side of the PDMA. Okay, so this is the complete PDMS chunk, which is now cured. You can see that it's quite thick. Okay, and the surface on which we wanted this microfluidic device to be embedded is actually the thinner surface side, and so what we have to do is a slow retrieval of these PMMA laser micro machine PMMA from the PDMS from the lower side. One has to be extremely slow in removing it, because otherwise there may be a stiction it has an irreversible seal which is developed on the surface, and so this stiction may be able to cause damage to the device structure. So, this is how now the device looks like. There is a thin film of the PDMS on the top of this surface. This is a thin device. We will also subsequently show a thicker version later on. You can see that you can see the mold not being separated. So, the mold is on one side and the other side is infiltrated with PDM. On the top of that featured side or pattern side of the mold, there is a rubberized PDMS which is left over. So, you can now separate the mold from that PDMS in a very careful manner, and the thin layer of PDMS which is now replicated can come or can be retrieved from the top surface of the mold, which is the patterned surface. So, the idea is whatever features are embedded within this die size that you now want to remove the PDMS, the replicated PDMS from the surface of the mold. And I would just like to illustrate here that in the laser micro machine PMMA surface there was a feature which was actually like a channel, engraved channel on the top of that the PMMA, and we are now replicating that channel. So, whatever we will be getting on the top of this PDMS surface will be a ridge. It will not be a channel, but will be a ridge, because now the PDMS has infiltrated into the pattern and we are separating the rubber and gotten rubberized. So, we are separating the rubberized PDMS from the pattern. So, it will have the same shape embedded like a ridge on the top of this PDMS layer. So, you can see this layer of PDMS being retrieved off the mold, which has actually the embedded feature, I would say the ridge like feature of whatever was like in embedded inside the PMMA or on the top of the PMMA. So, it is exactly the inverse, okay, of that embedded channel. Okay. So, this film has now something coming out of the surface, projected out of the surface like a ridge pattern of which is a replica of the pattern which was there on the PDMS. Okay. So, again reiterating, the PMMA surface which was laser machined earlier had a channel like depth in this particular shape and orientation, and the PDMS surface which has come out has the exact ridge like projected part of the surface coming out in those regions, okay, as you can see here. Okay. So, this ridge is actually being further replicated now in another layer, and that is why this process is called micro replication by double inversion. So, the first layer is the PMMA, is the channel, okay. The replication or replicated layer is the ridge, and this ridge is now again being replicated into a channel by using this ridge pattern on the PDMS after solidifying and heat curing the PDMS for some time, okay, as a ridge which would be finally eventually trying to take, you know, or create a replica of a ridge which is again a back to channel. So, we are actually inverting the pattern once, building a negative pattern on the PDMS intermediate, and then on the next step we are bringing another inversion of the pattern on the PDMS. So, we are essentially replicating a channel onto that surface. So, we will now demonstrate another very interesting the portion where we will be doing the secondary level replication by the PDMS film which has been extracted earlier with the ridge like pattern on the surface. You can see the ridge like pattern of the PDMS on the surface in this particular area. Okay. This again coming again, this is a channel, it is an embedded depth on the laser micro machine surface. This is the replica of that channel which is like a ridge or a projected out feature on this PDMS, and the next layer would be again replicating this particular ridge which would again be a channel on the PDMS surface. So, the first thing now what we have to do is to sort of heat this PDMS using a hot plate to a temperature of above about close to 200 degrees Celsius, where it becomes glassy, okay, because it is highly porous PDMS, otherwise it is very porous on the surface, and we want it to become glassy, so that this mold which is being used for the next step for micro replication by double inversion, this mold should be able to again be able to get separated very fast from the surface which it would itself replicate. So, we set up the temperature all the way to about close to 200 degrees to 202 degrees Celsius and allow it to heat cure the PDMS for this amount of time for about close to tens of minutes, so that the PDMS achieves a glass like structure on the top. So, now you have not only a ridge like structure on the PDMS, but you are making the ridge like structure very glassy, so that you can actually be able to replicate that glassy structure onto another layer of PDMS. So, we now the next step would be using the same desiccator for whatever glassy surface has been obtained. We will like to replicate that surface, so we have to use a mold release agent on that surface. So, now we will be actually taking on the PDMS structure and using the desiccator, okay, as we showed before in the last experiment when we were doing this replication of the PMMA mold. This is that PDMS with a ridge like pattern as you are seeing here, and we have to, this is glassy also because you have heat cured this whole surface, so it has become glassy. So, now you actually put the glassy pattern inside the desiccator, okay, and heat cure this with and chemically treat this with HMDS, hexamethyl disilazane, so that again the glassy surface of the PDMS that has been created can be coated with suitable hydrophobic layer. So, the HMDS normally comes in small ampules, and a very good idea for the process to take place. Mostly this process has to be in a sort of vacuum, in a sort of laminar flow hood like condition, and this vapor has to be somehow bleeded out of this desiccator again into the exhaust output of the laboratory. So, this is an ampule, so you have to very carefully crush the ampule, okay, and keep this ampule inside the desiccator, okay, and then close the desiccator and turn the desiccator on, so that whatever environment is being created here would remain for some time, and there would be treatment based on that environment. So, you can switch on the vacuum, okay, from the pump, which will make the desiccator stable, and now the idea is that you can make, this has become under vacuum as you can see, and whatever vapors are being generated by the HMDS now are going to fill this whole chamber up here, and they are going to sit on that PDMS mold that we had created, the ridge like film that we had created, and they are going to actually make the surface, the glassy surface of the PDMS ridge hydrophobic, okay, so that you can use this for subsequently another molding step following this. Meantime, you start preparing the PDMS mix again for the second round of replication. Remember, now you have to do the ridge which has been formulated in the last step to another channel now. So, it is the negative of a negative that you want to formulate. So, here now you prepare the PDMS mix as in the next step. So, you use that same process of measuring by weight, and there is a mold box, again a sacrificial mold box being used, and you will be using this this commercial brand available for PDMS by mixing two phases, which is the resin matrix along with the curing agent, okay. And this would actually be in a ratio of 10:1, so that by weight, so that you can have proper functionality like curing time, etc. Again, the curing time is realized by making by heat treating the PDMS to a higher temperature, okay. And so you can make the curing time shorter and shorter based on what is the amount of heat that is flowing into the system. Heat is like a catalyzer which would be able to cross bond the resin matrix and the curing agent, okay, pre-mixed resin matrix and the curing agent. So you basically measure and try to zero the weight, and then you can pour both the components, okay. So you have now poured the PDMS, okay. Now you will pour the curing agent to exactly 1/10 the weight. So you tear the system again and put 2.07 grams. While keeping an eye on the monitor, giving the weight measurement of this particular weighing balance. So you can actually pour exactly about 1/10, which is about 2 grams in this particular case, over the 20.7 grams of resin matrix which has been poured earlier. A good idea sometimes is also to use a dropper in this particular case, so that you can have exactly the amount which is being used, okay. And so therefore now you have a pre-mixed sample of resin and PDMS, which would now be doing the mixing with a normal stirring process, okay, using a clean stirrer. So in laboratories where stirrer are not easily available, etc., also you can use the a clean glass slide, to sort of mix both the PDMS as well as the curing agent. The only thing you have to ensure is the glass slide should be clean out of a packet, okay, and you ensure that the proper mixability is there. So while doing the mixing, there is an entrapment of all the bubbles, okay, within the PDMS, because it's a viscous fluid and it has some inertial delay. So wherever there is a scope, there is a tendency of the air bubbles to sort of get blocked, and it doesn't come out that easily, which involves the use of a subsequent desiccation step, which I have already illustrated earlier. So now the mold box is treated and ready. Okay, the vapor has all been coated on the surface of this particular mold box, as well as the PDMS membrane, which had the ridge-like feature. Okay, and now you pour the PDMS on the top of this particular ridge-like mold box. This is a pre-mixed resin curing agent matrix. Pour it in a manner so that it covers the entire pattern, okay, and there is a little bit of PDMS remaining on the top, which defines the film thickness that you would eventually need to use on the top of this material. So you can see already a lot of bubbles being entrapped on the surface of this the PDMS, and the idea is that you have to have some desiccation and some other steps so that these bubbles can be somehow gotten rid of, so that you can have a clear matrix, a visibly clear matrix of PDMS in this particular zone. There is always a sticking layer of PDMS to the bottom of the box, so it's a good idea probably to use whatever is left over, okay, and because this was by weight that you had made, envisioning certain height and dimensions of the final shape of the replica, okay, and so therefore it is a worthwhile really to sort of scrape off all the PDMS which was sticking to the surface of the box, so that you could actually pour this on the top of the mold, as is shown in this particular illustration. After the degassing step, and I didn't want to show the intermediate steps, but the PDMS has gone through that process of thermal curing, okay, so you have a completely rubberized matrix, where somewhere down the line here in the bottom of this particular area you have the mold box. So you have to now do the separation process and the retrieval of the replicated portion from the mold box, and for that you basically do the same operations. You cleave this box on the sides, okay, using ordinary paper cutter, and try to first retrieve the PDMS, the rubbery PDMS from the mold box. You can see that it is sort of it's come out quite easily actually, and you can actually trim off all the edges of this material. This material has to be cut and cleaved in the area which contains essentially the device part. The device part is quite visible, but although because now it is a PDMS over PDMS, the visibility has reduced a little bit because of the identical nature of the refractive indices of both the materials, but you tentatively know where exactly you have placed this device. You use a pre-cleaned glass slide, okay, to sort of try to use this as a jig to cut the PDMS straight, okay. You can see that we are trying to lay off by creating a hard surface, over which we will put this PDMS mold, and then use a glass slide as a guiding jig for the purpose of cutting off or scraping off the excess PDMS, okay. So we can actually now make impressions so that we are sort of trimming off the edge and trying to separate out the material which is not useful from the mold material, okay, which is somewhere inside. And in a similar manner you can do it on all the other sides or all the other edges, okay, by trimming them off. So this is essentially trimming off another edge, and so only that portion which will enclose or which would be containing the device will have to be retrieved from the whole stamp of the PDMS. This can be seen in this particular illustration. A similar chunk of the material can be removed from the other side. So now you have a piece, a central piece, where you have the two sort of the replica containing PDMS and the PDMS which has been replicated, just sitting one on the top of other. Okay, and then the hard process of sort of retrieving both comes to. Now remember, there is a glassiness of the surface which allows the easy retrieval of both the surfaces. Okay, as you can see here, there is a retrieval of one surface. So now we want to retrieve both the surfaces, and you can see the mass. We are trying to slowly separate the two surfaces together. One being glassy, it gets very easily separated, and the irreversible seal which is formulated between the replicated layer and the one which is the replica layer, okay, the mold layer, those get you have to really remove it carefully, so that such a reversible seal may not be able to cause a damage of the replicated layer, okay, while retrieval from the replica or the mold layer. Okay, so you can see how carefully, so all the edges have to be trimmed off, and how carefully the retrieval process takes place. So you can now see both the layers sitting parallel to each other, and I would just like to now take off. So you can see that how this layer is coming off, and very carefully you have now separated both the layers. Okay, so now the layer which has been formulated right here, okay, is a replica of the ridge which was on this particular side, which we had done earlier through the earlier processing steps, and it is actually a channel. Okay, and this channel can be easily used for microfluidic applications, because you can actually bond this particular surface containing the channel to a glass piece. And before doing the bonding, you can actually, with a small syringe needle, laboratory syringe needle, prick small inlet outlet holes on both the sides, okay, so that there is a easy transference of fluids, and you can that way connect the fluidic device to the external world. Okay, and so you can typically do this drilling process by very slowly twisting the needle, so that a straight path of the channel can be created, okay, till it goes to the other side. Okay, so you have now needles pricking holes on both sides of this device. Fantastic thing about this is it's a rubbery material, so whatever small channel has been created across the thickness of this PDMS can be easily cut this channel, okay, or cut this port in the thickness of the PDMS. The advantage of PDMS is that it is a highly elastic material, so therefore if you put a small piping or a tubing inside this drilled hole, there is always a tendency of a self seal to happen between the thickness of the PDMS and that pipe or channel, the tube, and therefore you can easily, in a very leak proof manner, handle fluids into this small structure which has been embedded on the bottom of this PDMS layer, okay, and closed subsequently by a glass wafer. A similar drilling is done on the other side for ensuring that the device is connected to an inflow and outflow port. So you now have actually a device with inlet outlet ports. Okay. We want to irreversibly bond this wafer by exposing it to plasma, oxygen plasma. This is a Herrick plasma Escher, which is very commonly available in laboratory in order to make a RF, in a magnetically enhanced laboratory level plasmas. And you have a clean glass slide which you are placing with respect to this PDMS piece here, right here, with the replication on the top, okay, the pattern on the top, and you are exposing it to oxygen plasma because you want to introduce the hydrophilicity of the surface, so that there is irreversible bonding between one side of the PDMS, replicated side of the PDMS, and the lower glass plate. Okay. And these are some procedures associated with how the plasma system is operated. You have going in the power on mode, and then there is a vacuuming step which is there. So this plasma chamber is now connected with the vacuum. Okay. And basically you can look through these holes here to see if the plasma has been obtained. Plasma is like a flame. You will be able to see on this particular through these viewing windows or these viewing galleries. And the moment the plasma is formulated, you wait for a certain amount of exposure time. In this case it can be very low amount of exposure time, close to about 30 seconds or so, from the formulation of the plasma, and this you can measure using a stopwatch. Okay. The plasma typically is formulated after switching on the magnetic circuit or the magnetic coil, and waiting for some close to few seconds, tens of seconds. So waiting for a few minutes till the plasma actually gets generated. You will just about start to see the glow coming out of these holes shortly. So you can see the glow come. Okay, the plasma glow has come now, and you wait for about close to 30 seconds after this glow is there, and that ensures that your process is fully completed. This is how it actually looks like. The tube is all lighting up with the plasma, as you can see. So as this plasma process is complete, we can switch off the plasma, okay, and take out the samples. And then quickly overlay the patterned side of the PDMS to the exposed wafer surface. Okay. This is very important because you should know what is the pattern size of the PDMS, because you are trying to close that size for doing microfluidic delivery. So you have a microfluidic device now, okay, where you can do flow control on the surface of this PDMS. Okay. You can put the inlet outlet ports on both sides of this drilled holes that we had done earlier, and so therefore you can have a very good flow channel which may be only defined by the feature size that was there on the laser wafer or laser made PMMA substrate, which was only a few microns. Okay. So here we can do some characterization of this microchannel using fluorescence microscope or in the optical field using the bright field option. So here you can actually see how this channel would typically look like. This is how the microscope has been focused on to this channel. Okay. So you can actually get some good images, and this microscope has a scale, so it can do some metrology as well. You can actually get a very good illustration of what are the various widths of the device which are obtained over this particular channel. So you can actually measure from between any two places, okay, on a scale which is definable by the magnification lens or the magnification factor on the lens that you are using.